Today we will start with discrete probability distributions, and I feel this is where we get more into the mathematical aspects, more of probability theory. Counting is hard, man. With probabilities, like counting and sample spaces and whatever. When I see things that connect to calculus or differential equations or functions, my mind is at ease, and I know I can handle those mathematics much easier than having to guess at sample spaces and things like that. So, that's behind us now on probability. Now we're going to move on and upgrade our knowledge a little bit. We'll start with probability distributions. We're going to cover discrete, then continuous, and then one more chapter after that, and then we hit inference. So we're very close to our objectives. So I'll take it a little slow. I feel like I've been going too fast here, and as I'm designing these slides, and obviously I still commit mistakes. I had 2450 here, numerical methods. This is a mistake here that I need to fix now. Okay, so let me fix that, because obviously I'm self-plagiarizing my own template. I'm not plagiarizing, it's my template, I made it. So, okay, so this is chapter 5 in Warren, but there's also another textbook that I'm starting to inject into the discussion, and I'm putting the PDFs on Canvas. So if you go on the main Canvas page, you'll see a PDF link to chapter 5 in Warren, but then a PDF link to another book by Molnar, classic textbook on probability and statistics for engineers. It's a little math heavy, but it has more engineering focused problems. So I know one of the concerns you will throw at me at the end of the semester is like, oh, we need more engineering examples. And you're correct, and working on that, and we'll see more of those as we get to the end of the semester. But let's face it, probability and statistics is more fun with like biomedical stuff and medical things, right? Or gambling. I don't endorse the latter, but we might see more examples on medical. But I'll try to have more examples with engineering. Most of the engineering examples will be focused on like product failure, product development. You're making batteries, drywalls, light bulbs. What's the likelihood of hitting a failure, and so on. Okay. Now, at the end of this chapter, again, in initial list of objectives, which will be refined actually when you finish the chapter. That's the irony here, is that hopefully at the end you'll be able to define what we mean by a discrete and continuous random variable, define what a probability, and this blew my mind as I'm putting the slides for random variables, because I always thought a random variable is just a variable that can take on a random value, but there's more to it. And I redid the slides like 4 times between yesterday and today, just to challenge that concept, because you can do more with random variables than meets the eye. Define what a probability distribution is and what a cumulative distribution is, compute binomial, hypergeometric, and Poisson distributions and their associated probabilities. And honestly, one point here is also, why do we even need probability distributions? What's the point of them? It's to make my life easier and your life easier. We'll see why. Compute the expected value, variance, and standard deviation of discrete probability distributions. We know these formulas because we did them in descriptive statistics. Identify when to use which probability distribution. So you're presented with a problem. Is this a binomial, hypergeometric, Poisson? And then we'll see that the Poisson distribution models rare events and can approximate binomial distributions, which are more expensive to compute. And we'll hit all of those points. And then define what we mean by a probability mass function, probability density function, and also cumulative mass function and cumulative density function. Very easy stuff. Okay. So we will begin by a simple statement that probability distributions are nothing more than the frequency distributions that we saw at the beginning of class. When we did descriptive statistics, we had these frequency tables, right? And that's it. It's a frequency distribution, except that these are probabilities. So they're fractions. Maximum probability is going to be 1. Maximum frequency is going to be 1, right? So the numbers cannot go above that. So they're like normalized frequency distributions, okay? And that's it. There's nothing more to that, okay? Now, for example, suppose that you are playing a coin toss challenge. So you flip 3 coins together, and if all 3 coins are the same, so you get 3 heads or 3 tails, then you win $3.50. And otherwise, you lose $1. And there's no cost to participate in the game. So you go at a Renaissance fair, and you flip 3 coins. If you get 3 heads or 3 tails, you win $3.50. If you lose, if you don't get any of those, you have to pay $1. Okay. Now, what is the probability? Later, we're going to answer the question of should you play this game or not? Are you going to win on average or are you going to lose on average? We'll answer that question later. We're going to keep this problem floating with us. But now the question is, what is the probability of getting 3 heads or 3 tails in any given toss? So we know how to work this problem out. The first thing we do is come up with a sample space. So you could get head, 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 or head, head, tail, tail, head, etc. TTH, THT, HTT, TTT. Okay. Now, obviously, order doesn't matter here because I could get HHT is the same as HTH is the same as THH. So these 3 outcomes are identical as far as we're concerned. Okay, because order does not matter. Okay, so now we know the sample space. We can now calculate the probabilities. We have 4 options. The probability of getting HHH is 1 over 8 because the sample space is 1, 2, 3, 4, 5, 6, 7, 8 outcomes in the sample space. And one of the outcomes is HHH. So the probability of HHH, classical probability, is 1 over 8. The probability of HHT is 1 over 8 plus 1 over 8 plus 1 over 8 because there are 3 outcomes in the sample space. So we get 3 over 8. And the probability of TTH and HTT, etc. So the probability of 2 tails and 1 head is 3 over 8 as well because there are 3 outcomes like that in the sample space. And finally, probability of 3 tails is the same as 3 heads. It's 1 over 8. These are fair coins. The game is fair, etc. Okay, so we kind of know how to do this, but I just want to use this to build a frequency table and then build a frequency distribution and a probability distribution and then change some nomenclature along the way. Okay. Now, if we wanted to plot this, among other things, but if we wanted to plot this, so on the x-axis, I want to put, what do I put on the x-axis? HHH, HTH, HHT. How do I order them? Is that weird? Like, are those categories? I want, if they're still categories, I cannot do a lot of math with this. I want to turn those categories into a numerical value. Okay, so it's really awkward if I wanted to plot this because the x-axis will be weird. I mean, I can do it, I suppose. So on the x-axis, I'll have HHH and then any of the other HTT, THT, etc. And then it has a bar corresponding to it and so on. But I want to do something nicer. I want to convert those categories into numbers, actually, so I can work through this as a numerical, mathematical problem, not categories. So one possible alternative is to take that sample space that we have, so HHH, HHT, and so on, and map it to a numerical value. Each outcome in the sample space will now be represented by a numerical value. Okay? That's called an abstraction of the sample space. And one way we could do it, we could say, how about we track the number of heads for each outcome? So for HHH, that corresponds to a variable whose value is 3. HHT, HTH, THH, those correspond to a numeric value of 2, right? Because we're only counting the heads, and they're the same. TTH, etc., and HTT and THT, they are a value of 1 because there's only 1 head, and TTT corresponds to a value of 0 because there's 0 heads, right? So I'm trying to go from a name or a category, HTT, to a numerical value, all right? So we let x be that variable, call it x, and let it denote the number of heads in each experiment, okay? So you're rolling, one experiment is throwing these 3 coins together. So TTT will now correspond to x equals 0. That's the mapping. This is the mapping. TTH, HTT, THT correspond to x equal 1 because x is only tracking the number of heads, right? So any one of those outcomes corresponds to x equal 1. And then any one of these outcomes that have 2 heads corresponds to x equal 2, okay? And HHH corresponds to x equal 3. You could have said, I want to count the number of tails. Sure, count the number of tails. Hold that x, and it will be, but that is a different mapping. And will work just as fine, okay? So now I can create a table of probabilities that works only with numeric values. So when x equals 0, and I'll explain the nomenclature in a second, but just look at the probabilities. So when x equals 0, it means I have 0 heads. My probability of getting 0 heads is 1 over 8. That's PTTT. Okay, that's that guy up there. Then when x equals 1 is 3/8. That's 1 head. Probability of getting 1 head is 3/8. Probability of getting 2 heads is 3/8 as well. And the probability of getting 3 heads goes down to 1/8. Okay? Now, notice the nomenclature. There's this capital X, which denotes the variable corresponding to the number of heads. And the way we write this is, we write the probability of x equal to a specific value lowercase x. Don't confuse the two. This is saying that, we're going to call this a random variable later. This is saying that the probability of the variable I'm tracking equal to a specific outcome, this is it. And these are the specific outcomes. One outcome is 0 heads, 1 head, 2 heads, etc. So this is saying P of 0 is 1 over 8, P of 1 is 3 over 8. It's just a little different than traditional, what we use for function calls in calculus. It's common to put it as x equals 0 or capital X equal 1, etc., to strengthen the idea that this is a probability distribution and the capital X is what we're going to call a random variable. Now you can take this and plot it, and you'll get something similar to the plots that we did before. We're just doing a bar graph right now because our probabilities, they are fractions and they all add up to 1 as we expect for the probability. And now I can say, okay, the probability of, on this plot of getting 0 heads is whatever, 1/8, 1/8, 3/8, 3/8, and then 1/8 again. Okay, very good. And I'm using all of this just to, I know we did some of this, but I'm going to formalize the nomenclature now. X is called a random variable, and P of X is called a probability distribution. That's it. We've done this, but we've finally formalized what we mean by those. Okay. So now on to a more formal definition. A random variable is any function that assigns a numerical value to each possible outcome in a sample space. It's function or mapping. See what I did when I converted the categories of head, head, tail, tail, head, head, etc. into a numeric value, that mapping. That mapping is when you create a random variable, because we know the outcomes in these events are random anyway. Okay? But when you map them to a numeric value, that process is called when you're building a random variable. And there's not one way of doing it. You could have counted the number of tails, or you could have counted the total number of heads in all of the experiments, right? The sky is the limit. We're going to come back to that point later when we answer another question about whether you should play this game or not. Now, a random variable can take on continuous or discrete values. In this case, it took on discrete values, 0, 1, 2, 3. But in many cases, as we will see in next chapter, a random variable can be continuous, 0, 0.1, 0.1356, etc. So we simply call when the random variable is discrete, we call it discrete random variable. When it's continuous, we call it continuous random variable. We will use symbols like capital X, capital Y, capital Z, etc. to designate random variables, discrete or continuous. Now, when they take on a specific value, we will use a lowercase x or lowercase y or lowercase z, and we will write, as you will see moving forward, probability of capital X equal lowercase x, or probability of capital Y equals 0.1. This is to stress the fact that this is a probability and this is a random variable. The random variable corresponds to random outcomes in the sample space. How that correspondence is, you create that correspondence. It's a mapping. It's a function of the sample space. Okay, now in this chapter, we're only focusing on discrete random variables. Next chapter, we'll do continuous. Okay. Now, P of X is called a probability distribution. And it's simply, a probability distribution is simply a formula or a table. It could be a table. You might not have a formula. If you're documenting these experimentally, you might not have a formula at all. You just have a table. Okay? And you might be given tables. At the end of your textbook, there are tables for binomial, Poisson distributions, and other distributions, okay? So you can look up probabilities very quickly. A probability distribution is a formula or a table of values that returns or gives you the probabilities of every possible value x of the random variable capital X. So notice the difference. The lowercase x is the one event. The capital X is the random variable for any of these events. We say that P of capital X equal X is the probability of the event lowercase x, okay? We will also use symbols f of x, g of x, h of x, etc. to designate probability distributions. This also means that f of x is equivalent to the probability of capital X equal an event lowercase x. So for example, for the binomial distribution, it's common to call it B. B of x and a bunch of other parameters. For the hypergeometric distribution, we call it H, okay? Just nomenclature, all right? Now, probability distributions can be discrete or continuous. Obviously, if the random variable is discrete, then your probability distribution is going to be discrete. If the random variable is continuous, your probability distribution is going to be continuous, okay? That's kind of obvious. Now, in this chapter, we will only focus to discrete probability distributions. All right. Now, sometimes a discrete probability distribution is called a probability mass function. And, well, it's not all the time. I mean, we're going to exchange, though. We're going to use those interchangeably. If I tell you, here's the PMF for this random variable, then you immediately know that this is a discrete probability distribution called the probability mass function. When you use Excel or some of those spreadsheet software, and you're calling a Poisson distribution, it will ask you, are you going to use the Poisson PMF or the Poisson PDF? What is the PDF? Is when the distribution is continuous. We call it a probability density function, not Acrobat stuff. You cannot open the probability distribution with Acrobat. PDF, probability density function for continuous probability distributions. Okay. Now, for all distributions moving forward, they must satisfy the postulates of probability. And the two important postulates are that all probabilities are between 0 and 1 inclusive. So you cannot have a probability greater than 1 or less than 0, because it's a fraction out of a 100%. And the sum of all probabilities is exactly equal to 1, right? You add them all up together, you get 100% probability. Now, you might get sometimes a little bit larger than 1 because of rounding. That's okay. Don't lose sleep over it, all right? We will see sometimes we might get a sum of all of these probabilities. So essentially what you're doing, you're summing up the values in the probability table. Or when you are doing continuous, you do an integral. This becomes an integral of the probability of the PDF. But then you add them up. Sometimes you might get a value larger than 1 or less than 1. That's because of round-off errors, okay? And that's okay. All right. So now, together, we're going to build a probability distribution for the sum of two rolled die. And if you remember, this is the sample space that we had for rolling 2 die. The sums start at 2 and they end at 12, okay? These are all the outcomes. And obviously, because the outcomes are discrete, then we're going to have a PMF, a probability mass function, and we can put it in a table, okay, rather than a formula right now. For now, we can just put it in a table. So go ahead, take a stab at this. And first, you need to define x, the values for x, the random variable that corresponds to what? I'm telling you, your random variable is going to correspond to the sum of the 2 rolled die. So this is the first hint I'm giving you, is that your x values for the random variable start at 2 and end at 12. That's it. There's no 0, there's no 1, because it's outside of the sample space. So your random variable is 2, 3, 4, 5, 6, all the way to 12. So create a column, x, which is equal to the sum of the 2 rolled die, list the values, and list the probabilities for each of those. Remember, the probability is simply you divide the number of outcomes for the event over the total in the sample space. The sample space has 36 outcomes in total. Go ahead and try it. So for x equal 2, you have only one outcome. So the probability of getting x equal 2, the sum of 2 is 1 over 36, okay? Then go to sum to x equal 3. Just list them in a table. Sorry. You should see that the probabilities go up and then they come back down, right? The total outcomes in this sample space is 36, so your denominators are going to be 36. Okay. So if you've done this, go ahead and try to plot it in your Google Sheets if you want. We'll do some plotting a little later. But if you want, just go ahead and plot it in Google Sheets. Plot it just as a bar chart. Don't worry about the bars being next to each other. That's okay. All right, so what did we get? If I'm right and if you're right, this is what I would get. For sum of 2, I have only one outcome, so the probability is 1 over 36. For sum equal 3, so when x equal 3, I have 2 outcomes out of 36, and so on. You see the probability peaks at a sum of 7. You have the most outcomes at 7, 6 over 36, and then it goes back down. Visualizing is a blessing. Our eyes are like, what, 80% of our senses, right? Visualizing things is one of the best things you can do. Here's a plot of this probability distribution. On the x-axis, I have the sum of the 2 rolled die. Okay, so 2 to 12. That's it. That's my entire space. There's no 0. There's no 13. Right? The probabilities of those are 0. They don't exist. Okay, and on the y-axis, I'm plotting those probabilities as a fraction, right? Okay, so 1 over 36, 2 over 36, all the way, and they peak at 7, and then they go back down. Okay, so this is a symmetric plot, if you remember, etc. Okay, great. We've done this. We've done this. We've put some formal definitions. Let's move on. I want you now to open your minds about random variables. Okay, and I'm going to help you open your minds, because I opened my mind also earlier this week. So now I want to answer the question. Well, first I'm going to make a statement, obviously. You must be creative in how you assign your random variables. Remember, they are simply a mapping of the sample space. So you can map it in whatever way that is convenient for the problem that you are working with. So here's the example again. Let's go back to the coin toss game. Okay, so we're tossing 3 coins. If you get 3 heads or 3 tails, you win $3.50. If you get anything else, you're going to lose $1. You have to pay the kiosk $1. So if you play this game a number of times, are you going to come out winning or losing? Okay. Where do we even begin starting to answer this question? Let's go back to our probability distribution for this problem. Well, you could say, okay, looking at this, there's a 1/8 chance, there's a 2/8 chance that I win $3.50, and 6 over 8 chance that I would lose $1, right? That's the probability essentially of winning 3.5, probability of losing $1, probability of losing $1. So you combine them together. But it's still weird. Like, what am I tracking? Number of should I worry about the number of heads or tails, or should I worry about how much I'm winning and losing? Does that make sense? This problem is about winning or losing. I don't care about the heads and tails anymore. So how about we ditch this guy and create a new random variable about earnings? Can I do that? Absolutely. Yeah? It was a question I'm answering myself too, but go ahead, share, yeah.
You could just combine the outcomes win and the
Agreed, 100%. But what I wanted to use, so what your colleague is saying, yeah, we just combine the winnings. So you have 2/8 chance of winning 3.5 and 6/8 chance of losing $1. But what does this mean? Should you play this game or not? Are you going to come out winning or losing? How would you calculate that number? So the first step to getting there is to ditch this random variable and instead create a new random variable that's based on the earnings. So the purpose of this problem is to tell you that you can create a random variable in any way you like, as long as it helps you answer the problem. And I guarantee you that if instead of x, this number of heads, we focus on the earnings, that is going to get us closer to answering this question, because the earnings are going to be a better random variable to describe this problem. So instead of working with the number of heads, I'm going to work with the earnings, all right? So I'm going to change this distribution, and I'm going to create a new random variable that maps the number of heads and tails in the sample space to earnings in the game. So I create a new random variable, call it W for winnings, or E for earnings if you want. And I could either win $3.5, and the probability of winning 3.5 is 1/4. And the probability of losing $1 is 3/4. Okay, so I have now created a entirely new distribution, new random variable that has only two values on the x-axis, -1 and 3.5, so it's discrete, and with associated probabilities. So now, if I plot it, this is what it looks like. And when you look at this, you're like, crap, maybe we're going to be losing more because there's, there's more chance of losing than winning. But still, how do you get that number? So let me ask the question in a different way. In this game, you have a 25% chance of winning $3.5 and a 75% chance of losing $1. Should you play this game or not? Well, how would you get to that number? If you take 25% times 3.5 plus 75% times -1, wouldn't that give you your odds of winning or losing? Like how much you're winning or losing? Because 25% of the time I'm winning 3.5, and 75% of the time I'm losing $1. So if I multiply 25% by 3.5, that gives me the weighted cost of the weighted winnings, how many times I'm winning, minus 1 times 75%, which gives me also the weighted loss. Wouldn't that give me an answer for how much on average I'm winning or losing? If you do this, you're actually winning 12.5 cents per game on average. So I would play this game, probably play it 500 times for it to be worth it, right? Now this doesn't mean you can have 50 times back-to-back you're losing. But on average, in the long run, you will be winning on average 12.5 cents. Okay? If we get a chance, we'll do a casino game, a casino example one time with the roulette. You see, like the roulette, the house wins on average about 7 cents per game, which is nothing, but multiply that by the number of tables and the sheer number of people playing this game, that could result in millions for the house. You just need a little bit, because for 7-9 cents losing, it's not a big deal. I'll take my chances, right? But for the house, it's huge. Okay? So this one is winning for you, right? Now what we did here, we know how to do this. This is not new. This is called a weighted average. What we did, we took the average of our distribution, or our earnings, $3.5 and minus $1, and we weighted them with the frequencies. We did that before in descriptive statistics, except now we're using them to make a prediction. Okay, make a prediction of whether this is going to be a winning game or not. Okay. Now, when we're dealing formally with probability distributions, not just frequency distributions, we call what we did the expected value. What is the expected value? Is what you expect your random variable to give you on average after a long run of experiments. Now, because this problem required me, if I did the expected value on the variable x, which counted the heads or tails, my expected value is going to be a result in number of heads or tails, not in dollars. But when I converted my random variable to dollars, then my expected value is going to be in dollars. And that's what I want. That's the answer that I want. Okay? So the expected value of a discrete random variable is equal to the mean of the probability distribution x. And so it's a weighted mean. So it's simply the summation of the individual random variables times their probability, right? So it's a weighted average. And that is consistent with the mean value. So we give this mu. This is for a population, like we discussed at the beginning. And it's simply the summation of x, all the x values times their probabilities. So like we did, 25% times $3.50. So x was 3.5 times 25% was the probability, plus minus $1 times 75%. Okay? All right, so let's do this example. Maybe we'll do this in Google Sheets. Jafar is trying to decide between two different investment opportunities. The two plans are summarized in the following table. Okay, so plan A, there's a probability of earning $1,200, 10% probability earning $1,200, $950 is 20%, earning $130 is 40%, losing $575, there's 10% chance, and losing $1,400, there's a 20% chance. And there's another plan, got $1,500, 30%, odds of winning and losing. Okay, now we want to help him decide which plan he should choose and which one has more risk, actually. Okay, so what do you do in this problem? You go immediately to the expected value, because that gives you, on average, as you invest in one of these plans or as you play this probability game, okay, this game of chance of investing in this, it gives you an idea of, on average, how much you're going to be making or losing over time. All right. So we can go ahead and do this. Let's open up some Google Sheets. I was going to do this in Python, but I will leave Python discussions possibly for a little later in the course. They're quite involved. You gotta kind of grab your ear weirdly. So we'll strengthen our knowledge in statistics and inference before we jump on to probability, to Python. Sorry. Okay. So let's see. All right, so let's create a new spreadsheet. Go on Google Sheets. You can use Excel. You can probably figure out the thing in Excel pretty quickly. Okay, so apologize. I have to turn my head to you, my back to you, the back of my head, I guess. Okay. All right, tables. All right, so we have Plan A and the earnings in Plan A, we got, actually I have them here. So we got 1,400. Let's zoom in for those in the back. Is this better? Yes. Okay. 1,400, 950. Obviously, you can do this on your calculator or by hand. I just want to show you we'll just do it together in Excel. Google Sheets, minus 575 and minus 1,400. And the probabilities were 0.1, 0.2, 0.4, 0.1, and 0.2. So this was Plan A. Okay. And actually, I'm going to go to Plan B. I'm going to leave this column empty here because I'm going to need it later. Okay, we'll leave two columns. And then Plan B, okay, earnings, and then probability, or probability, okay, probability. This is nothing fancy, really. Okay, so 1,500, 800, minus 100, minus 250, and minus 690. And I guess the lesson here, don't judge a book by its cover, because just kind of looking at those numbers, I'm like, yeah, I don't know. There's I can't tell really, but with Plan B, there's 3 rows with losses. I don't know, but this one has more. I can't tell. I really can't tell. I have to compute the expected value. All right, so let's do that. I'm going to create here, let's call it expected value. Now, don't use the average function in built-in Excel or Google Sheets because that's just going to give you an arithmetic average. Here we want a weighted average. So there's two ways of doing it. You either implement it by hand, so do the product together and sum them up, or use a weighted average built-in function, okay? Now, what we want is summation of, so let me get my slides back, summation of x times the probabilities, right? So what we want is summation of xi times p of xi. So what that means, I need to multiply this column by this column, one by one, and then sum up the answer. Now in Python, we used to do this automatically. Array A times array B, right? It multiplies them element-wise, and then we take their sum. Okay? Google Sheets or Excel is not going to be able to do that because you cannot just come and say sum of a product. Sum here is going to be, you have to build the product separately. So you could say, one way to do it is say, I'm going to take the products here times this guy, and then run it all the way to the end. So this is xi times p of xi, right? And then you sum it up, sum of, oops, it should automatically figure it out for me, sum of these guys, okay? And that will give you, hold on, summation of x, that doesn't make sense. Did I miss something? 0.4, 0.1, 0.2, 1400, 950, 130, 175 minus 1400. I made a mistake. Sorry, I made a mistake. It should be 1200 here, my bad. 1200, okay. So this says that the expected value is $24.50. So on average in this plan, investing in this plan, Jafar is barely making money. $24.50 is insignificant, okay? All right, so you could do it this way, or, so that's method number one. Instead of having to create a new column, etc., you can use what's called sum product. There's something called sum product. You see that? Sum product. It's sum of the products of elements in two arrays. So it's going to take array 1, and then you put a comma, and put column 2, and there you go. You get the same value, but this one does it internally, does this product for you internally, so you don't have to create a new column. Okay? So you don't have to create a new column. Okay, so I guess I can keep this or just delete it. All right. Another way is called the weighted average. So this is a weighted average, and these are the values. The earnings are my values, and the next array is going to be the weights. So this is identical to a sum product and gives you 24.5. 3 different ways of doing this. Okay? All right. So let's go for plan B. I don't know, okay, we can't keep the weighted average. So let's copy the weighted average. Actually, I'm just going to drag it over there, and it should figure it out by itself. So delete these guys. And look at plan B. $322, that's not bad. That's a good, given the investments, 1,500 to buy, so that's kind of in the ballpark. You guys doing 20% return. So that's a far better plan, I think. So that would be a winner in general. Okay? But it doesn't evaluate risk yet. So, okay, we know that probability distribution, but we want to see how much of a spread there is in this, right? How much variability is in these data? Okay, are these going to be, 322 on average, but there's a chance of losing everything or winning a lot, right? Or everything is kind of all the investments are clustered close to each other, or the returns. So to do this, we have to assess the variance of the data. And similar to what we've done early on with descriptive statistics, we can define the variance of a discrete probability distribution. We'll have a similar definition for PDFs, but for PMFs, the variance is given by either one of these formulas. They're the same. Now you're doing summation of xi squared time weighted by the probability, or xi minus mu squared. Remember, the variance is the distance from the mean, measures the average distance from the mean. So you have xi minus mu squared time weighted by the probability. Now, Google Sheets does not have a function that does that. Even if you call the var function, it is not going to compute mu correctly, because mu here is a weighted mean of the probability distribution. The variance computed in Google Sheets is going to be based on the arithmetic mean, which is wrong. So you have to manually compute this variance, then take the square root to compute the standard deviation. Be very careful about that. There might be statistical packages that you add to Google Sheets or Excel that would give you, but be sure that it's using this formula. This mu over here needs to be based on the weighted mean, on the expected value. Summation of x times the probability, xi times probability of xi. Okay, so we're going to implement this formula ourselves. We do variance, all right? And now I need the xi squared. So I need to create a new column. That's why I wanted a new column. So xi. And that is going to be x times x. All right? Do the thing. Okay. What? No. Not b3 times a3, silly. All right. Just. Okay, a3 times a3. Leave me alone. All right. Jeez. Okay. So now that gives me xi squared. And now for the variance, I'm going to do, remember, so I can do either do xi minus mu squared, all right, or I can do this formula. So yeah, let's do this formula, because then I can use a sum product here. So what I'm going to do here is a sum product of xi squared times the probabilities, so comma, the weights, these are the probabilities, minus the expected value squared. So, and that gives me, whatever, $755,722 squared. Okay? So the variance is in the units of the variable squared. Right? And we can do the same, and then we can do the standard deviation as standard deviation, and that's equal to the square root of the variance. Pardon me? Square root of the variance. You got $869. So the spread in the investments is about $869. That's very, very large compared to $24.50. All right, so that's quite the spread. So there's some risk involved. And it's almost half of the biggest earnings or the biggest losses. So, this doesn't look very good. There's a huge risk. Let me get this all the way here. Okay, so I need to compute the variance. I need to compute the xi squared over here as well. So xi times xi. And what I will do is, this is equal to earnings times E3. All right. Okay, so now the variance here is $745,000. It's less than the variance of plan A. They're close, but it's less. Okay, so then the standard deviation is the square root of that variance. Oops. Yes, keep adding parentheses. Okay, so the standard deviation about the same as plan A. So what should we do here? Jafar has only these two plans, A and B. They're both about the same risk, because their variance is just about the same, their standard deviation about the same. But one of them has a larger expected value, so go for that one. It's a no-brainer, right? If these are the only two plans he's presented with. Agreed? All right, so probably there's a mix of investments in both. Some of them are the same. Okay. Now, that's not the way to spread your risk. Okay, so spread your risk. You adopt modern portfolio theory if you're into investments. You balance some high risk, low risk, international, local, etc., stocks and bonds. But the most important things that plays for you in investments is your age. The younger you are, the more risk you can take, because your plan for investments is to only use them when you're like 90 or never use them at all. So your timeline, or 70, let's say. If you have 40 years, go stock market. So, if you're 20 now and you have 40, 50 years of investing, then just go total stock market and forget about it, okay? And enjoy the great wealth that this country can give you. Okay. All right, so we figured this out, blah, blah, etc. Okay. So why work with probability distributions in the first place? So far, we've kind of observed, we built our probability distributions based on observations. But what's going to come next is we're going to identify some pre-built probability distributions, and we're going to use them to model different things. Let's resume. Why do we work with probability distributions? And so far, we looked at probability distributions that we built based on one particular problem. But the cool thing that we're going to do is we will learn about a few probability distributions that are well known, okay, like the sine function or the exponential function, right? And you use them to model things. In probability theory and statistics, we will do the same. There are some distributions of probabilities for any random variable that work so well for certain problems, and you can use them to model those problems. And what it does for you, it spares you the nightmare of having to count your sample space, count your probabilities. It gives you the advantage of working with a mathematical formula for the probabilities and their cumulative probabilities, how to do all sorts of analysis on a certain problem. So it really elevates simple probability risk analysis, okay? Yeah. Now, for example, is a process governed by, okay, so for example, rolling a die, so sorry, I was putting these slides before coming to class, so. So for example, rolling a die, okay, so for example, rolling a die is a process that is governed by what is called the binomial distribution. So moving forward, whenever you have a die problem, whether you roll it 50 times, 7 times, 125 times, and you ask a question, what's the probability of getting 5 consecutive number 3 or whatever, you don't have to go back to the drawing board and build the sample place, calculate the probability. You just use the binomial distribution. And you plug in the parameters, and bam, you get your probabilities. So they're really powerful. Okay, so we will learn about 3 distributions. We'll probably just be done with the first one today if we have enough time. And the first one is going to be, we call it the binomial distribution. Okay? The binomial distribution models situations. So I say models because sometimes it's not an exact science. When you look at a process that's happening, you say, okay, I'm randomly picking, drywall from the assembly line and putting it back, right? Maybe you can approximate that with a binomial distribution, and then you move on, right? So I say the word model, but sometimes it's an exact representation of reality, okay? So I use the word model, situations with a fixed number of independent trials or experiments, where each trial has only one of 2 possible outcomes. We call those success or failure. So again, rolling the die, and what is the chance of rolling the die 100 times and getting 7 number 2? Or what is the chance of flipping a coin 200 times and getting 20 heads in total? This is what the binomial distribution does for you. If I were to ask you that problem, do the probabilities, you're going to be like, oh my gosh, where do I start? What's the sample space? What's the probability here or there? Binomial distribution does that for you. And the best part is that all you need to know is the number of trials, and make sure that you only have one of 2 outcomes. So heads or tail, or like success or failure. So although in the die example, you have 6 faces on the die. 1, 2, 3, 4, 5, 6. But the question is, what's the probability of getting 2 15 times? That's success. Everything else is failure, right? So you have 2 outcomes, success or failure. What's the probability that the drywall that you're picking from the assembly line, you get a sample of 100 drywalls, what's the probability that 7 of them have a puncture in them, right? That's success or failure, okay? Now, you can define success as getting the value you want, or the other way around, doesn't matter for this probability distribution, okay? The random variable in this case tracks the number of successes or failures after n trials, or n times you're running the thing. Now, for example, what's the probability of getting 16 heads when tossing a fair coin 58 times, okay? In this example, we're tracking the number of heads, which is the random variable x, and that is our success. So anything that's not a head is a failure. All right, so we define it formally. Binomial distribution is a discrete probability distribution with a fixed, it's very important to recognize that this is a fixed number of independent trials, okay? And now we have to list some conditions for when you can use this. Where each trial has only 2 possible outcomes, and one of these outcomes is counted. So either success or failure, okay? So think about it this way. For simplicity, we call them success or failure. It could be the number 2, it could be heads, it could be tail, but just call it, if you get what you want, it's success. If you don't get what you want, that's failure, okay? Now, the formula for this probability, I'll explain the numbers later. You have n choose x, where x is what you're tracking. So 16 heads, or 5 number 2 in the die problem, right? P is the probability of, is going to be the probability of getting success in a single trial. So if it's a fair coin, you get 50%. P is 50%. Okay? I'll explain that in a little bit. These are the rules. The experiment consists of a fixed number of identical trials. So you're tossing the coin. You toss it once, you toss it twice, 3 times, n times you toss it. Each trial is independent of the others. So for example, if you're looking at the assembly line, checking if your batteries are damaged or not, you have to put the batteries back. Okay? So this is with replacement. Otherwise, you're going to influence the next trial, right? So your trials need to be independent. Okay? For each trial, there are only 2 possible outcomes. We call one outcome success and the other outcome failure. Again, the outcome could be heads or tail. We call heads success, tail failure. So we don't get into the specifics of the problem you're dealing with. Okay? For every trial, the probability of getting a success is called P, and the probability, therefore, of getting a failure is 1 minus P. P is usually known. So for a fair coin, P is 50%, for example. Or you buy from experience and knowledge on in your LEDs, you're building LEDs, you have a chance of 10% failure, okay, if you're randomly picking LEDs from a sample, right? So that becomes your probability P. The binomial random variable x, this is very important, on the x-axis, what we're counting the number of successes in n trials. So when we're going to plot this distribution on the x-axis, we're going to have 0 successes, 1 success, 2 successes, 3, 4, 5, all the way up to the n trials. Okay, you cannot have more than n successes in n trials, right? Because that's n trials maximum. Okay? And finally, this is the power of having a formula for this. We know the mean is simply n times p, and the variance is n times p times 1 minus p. So you have formulas for those. You don't even have to go and calculate them in the tables and whatnot. You just have math. You're dealing with formulas. Simplifies the world a whole lot. Okay? This is the formula for the binomial distribution. Probability of your random variable capital X equal to an event X. In this case, lowercase x counts the number of successes in n trials. So the probability of getting 5 heads in 50 coin tosses, then lowercase x is equal to 5, okay? That's how you're looking at this. And n is the number of trials, x is your number of successes you're tracking, p is the probability in a single trial of getting success. So the first thing you want to do is define what success means. Okay? We also write the binomial distribution as b So like I said, we use different symbols. Instead of using p x equal x all the time, we can write it as lowercase b. X counts the number of successes. You have a semicolon. And because this distribution depends on two quantities, n and p, two parameters, in other words, you put np. So sometimes you're presented, okay, here's your binomial distribution, bx, 50, 0.7. So it tells you have 50 trials and a probability of 70% of success per trial. Okay? So let's go ahead and plot this binomial distribution together. Okay, I'm going to make up a fictitious example, or like just a made-up example. Pull up your Google Sheets. We can do this totally in Python, but we're going to do it in Excel now. So pull up your Google Sheets. Let's create maybe a new spreadsheet, plotting the binomial distribution. Okay. So let's start with the simplest problem ever. It's a coin toss, okay, and I want to toss it, what, 20 times? Okay, 20 times. So my random variable is going to, and I call success is getting heads, okay, just for the sake of the argument. So my random variable is going to track the number of heads, okay, the number of heads up to 20 trials. Because at most, I can get 20 heads in 20 trials, right? All right, so my random variable, I'm going to call it x, okay, is going to start from 0. Actually, I'm going to do, so we can do 0, 1, 2, right? Or you can do something cool and say this is equal to sequence, and I'm going to start, sequence 8, 2. No, sequence 8, 2. Okay, I'm going to do one column, and I'm going to start at 0. Oops. No, circular dependency detected. Of course, circular dependency is going to be detected. Hold on. Let me figure this out. Sorry. This is the number of trials. So let's say 20 trials. Okay, and we're going to start at 0. So when you do this, so if you think here, sequence, this is going to create 20 entries starting from 0. Okay? However, it only goes 20 entries from 0 to 19. That's 20 entries. So I really want my last trial or my last value to be 20, because at most I can get 20 successes. Okay? So I'm going to up this by 1. So I'm going to do sequence 21. So I can go from 0 to 20 over here. Okay, let's make this a little smaller, 90% or 100%. Okay. All right. So now I want to calculate the binomial formula. All right, and we're going to assume we already picked n, the number of trials. It's going to be 20, all right? So my x values, my random variable, which counts the number of successes, how many heads I can get, is at most 20, okay? So I created that in that first column. Now I need to define my probability of success. Let's start with a fair coin. So with a probability of success, 50%, okay? So we're going to do here, I'm going to call this p, and I'm going to put it 0.5 over here, because I want to change this later to see how the distribution changes. And here we're going to put the PMF of x. Okay? And luckily, you don't have to program this by hand. Google Sheets, Excel, even Sheets on Mac OS X, numbers, sorry, on Mac OS X, has a built-in binomial distribution. Okay? So we're just going to use that. You put equal sign, and you type in binom dist. Okay? Now, look at these two things here. There's binom dist or binom.dist. They're both identical. Okay, they're both the same thing. They use binom.dist for legacy reasons because Excel uses that. And they want it to look the same, but they're identical functions. Okay, I just use binom dist. Now, when you select it, look at that. Number of successes, which is our x value. 0, 1 success, 2 successes, 3 successes, 4 successes. So we're going to look at the number at all possible number of successes up to 20. Okay, so in our first argument, it's going to be this column, so the A value. Number of trials is going to be that last number, 20 over here. The probability of success is going to be this guy here. Cumulative, we're going to talk about this later. Right now, we're not doing cumulative. We're just looking at probability. So don't worry about cumulative for this. So what we're going to put here is the number of successes. So we're going to put this one here. Okay? And then the next value is going to be the number of trials, which is 20. Or I can put here number of trials, and trials is 20. So just keep track of that. Okay, so you can point to this guy over here and put dollar signs so it doesn't change as we drag this down. Probability of success is F2, F2, and cumulative false. This is not cumulative. This is not a cumulative distribution right now. Okay, you do this, ta-da! It gives you all the probabilities. Okay, all the probabilities. So this number here is the binomial probability. Let me zoom in a little bit more. Okay. This number here is the binomial probability of getting 0 successes. Okay. This one here, 0 successes in 20 trials. Okay. 20 trials. This one here is the probability of getting 1 success in 20 trials. And so on. What is success? Is getting a head. Okay? So getting 0 heads in 20 trials, getting 1 head in 20 trials, getting 2 heads, 3 heads, 4 heads, getting 5 heads in 20 trials, and so on. Right? Now, the best way to do this is visualize it. So we're going to go select these 2 columns and go insert chart, and it gives you this distribution here. Because this is discrete, I want to make it into a column chart, actually, like this. All right? Okay, beautiful. Okay, so what does this tell us here? On the x-axis, I have the number of successes in 20 trials. Always don't forget that. In 20 trials, how many successes do I have? What is success? Is getting a head. In other words, the probability of getting 0 head is almost 0. Probability of getting 1 head is pretty low. Probability of getting 2 heads. 5 heads is just this number. Probability of getting 7 heads. 8 heads starts to growing. Probability of getting 10 heads is at the peak, right? And then it starts going down, right? That's how you interpret this distribution. Make sure you understand the x-axis. X equal 10, the value at x equal 10 is the probability of getting 10 heads in 20 trials. Be careful how you interpret this. Binomial distribution. So now this is cool because you don't have to go back and calculate probabilities. What's the probability of getting 17 heads in 50 trials? You can just change the numbers over here and it gives you that probability. It's incredibly powerful. Okay? Before we change, now if you want to put 50 trials, I have to change this row, this column here, and everything will change. We'll have to plot it again. That's fine. Or you can just evaluate it for one value. But what I'm interested here is, what will happen when I change P? So what if we go P equals 0.1? The probability of getting a head in a single toss is 10%. Or the probability is 0.9. The probability of getting heads is 90% in a single trial. What do you think is going to happen to the curve? Okay, 100%. Okay, let's start with 0.1, 10%. What do you think is going to change? To the left or to the right? Okay, more answers. So the question, pardon me? Yeah, so what I'm asking is, now we have this situation, 20 trials with a fair coin. There's a 50-50 chance I get heads and I get tails. What if there's a 10% chance that I get heads and 90% chance that I get tails? In other words, my probability of success in a single trial is 10% now. What is going to happen to this? Is it going to move? So Nicholas said it's going to shift either to the left or to the right. What is going to happen? Is it going to move left or right if we go 10%? Okay, why? There's less chances of getting a success, right? And because the X value tracks your number of successes, you have less successes. Okay, you're going to have less successes, so your probabilities are going to be stacked on the lower success end. Okay, let's test this. Maybe, did you test that on your Google Sheets? Okay, go ahead and test that. Okay, so let's test it. So our hypothesis now is that if the probability of success in a single trial is low, 10%, then that curve is going to move to the left. Why? Because we have less successes, therefore, most of the probabilities getting the most success is going to be a low number. It's going to be on those axes over here. And indeed, this is what should happen. Okay, so if we go to 0.1 here, look at that. All the probabilities went to the left side. The best probability of success is just barely 30%. There's a chance of getting 2 heads in 20 trials 30% of the time. There's a 30% chance of getting 2 heads in 20 trials in this probability, okay? So I guess I'm done. One more thing, so let's do 0.9. 0.9 means, oh man, you're going to succeed a lot. There's a much higher chance of getting, look, there's a chance of 30% of getting 18 heads in 20 trials. Okay? That's how you read this. All right, so we're going to build on this. It's a pretty cool concept, right? I guess you're all excited. I can see that. All right. I'll see you on Tuesday. Godspeed.